Okay. Okay, welcome guys to 22nd session of this AI. So today, as part of the big data engineering, we will be covering Apache Cassandra. I'll just give you a basics overview of Cassandra and then connecting the Cassandra to Spark and storing the data in the Cassandra, just like we did with Elasticsearch. The same thing we'll do with store the data into Cassandra. So I'll show you a couple of integrations, couple of pipelines where you can pull the data and put into Cassandra. So the agenda for today is that I will be discussing Apache Cassandra. Then we will have a session. I think Narayana and who else is with you, Narayana?
Hari.
Yeah, Hari. Okay. Yeah, Narayana and Hari will be doing the presentations and Hema will be moderating it. So we will discuss Cassandra first and then we'll take a break. After that, you can do your presentations. So probably I will finish it early today, a little early. So probably you can take over from there for your presentations. So bear with me, my voice could be a little low today as I'm fasting. So let me know if you have face any issues during the presentation, if you're not able to hear me or something. Okay. Just give a couple of minutes and then we'll start. So before that, I wanted to check how we are doing with the big data engineering track. So are you guys started Eclipse and practicing the programs with Spark programs, or at least the Spark SQL files, reading files and writing data? I just wanted to check Leela and Hari.
Harun, I did not do it. I did the setup, but I have not yet done. I'll do this week and I'll let you know.
Okay, sure. No
Yeah, I'll also try probably a couple of weeks. I will travel into the coming weeks. I will try and practice more.
Okay, sure, no problem. Yeah, whenever you get time, I guess you have all the videos and you also have, I've posted the jobs on the Facebook. If any programs you don't find, just ping me offline. I'll upload the same onto FB, or what I will do is I will zip all the programs I have and then I'll send it to you. So you can use those programs for practicing your jobs. Okay.
Okay, thanks, Harun.
Yeah, sure. Yeah. Okay, so let's get started. We have 15 minutes into it. So today we'll discuss Apache Cassandra as part of our big data platform engineering tools. So we have seen different tools just in the big data platform connecting Apache Spark. We have seen Elasticsearch, we have done Twitter, we have done Kafka, HDFS, Apache Hive. So in the big data platform, so there are so many data stores or databases that you can connect to with Apache Spark, right? So as we said, we are exploring a few. This both Spark can connect to RDBMS, our traditional RDBMS like Oracle, MySQL, using the connectors or the Teradata. and it can also connect to the data stores like Elasticsearch or NoSQL databases like Mongo, Cassandra, Couchbase, etc. So we will explore the Cassandra, and then you can also go ahead and as part of your if you want to explore more, you can try connecting with different databases, NoSQL databases like Mongo, etc. So basically, whatever you store as a data pipeline, it's the same. You have a source, you have processing with Apache Spark, and then you persist the data. Either you persist in a data store like Elastic, search engine, or you store in the NoSQL database like Cassandra, or you store in a RDBMS like MySQL. It's all the same. So it's all the same thing. It's all different targets or the destination where you want to persist the data, right? So based on that, what we have explored so far in the data pipelines, starting from data ingestion tools, we have seen like Kafka, STFS, Twitter, then processing with Apache Spark, both batch and streaming. And then we have also seen how to persist the data in the Elastic. So we can also do it with the same pipeline connecting to the Cassandra. So Cassandra is a NoSQL database, okay, which is much similar to your RDBMS, but it differs in how the data is stored, in how the data is modeled, and how the data is distributed, right? So it's a free and open source distributed NoSQL database management system. So it's a NoSQL database and it's open source. It is designed to handle large amounts of data across many commodity servers, which means any cluster distributed system database, you have clusters. You have multiple machines that form a cluster, right? And each machine or node forms a cluster, part of a cluster. So you can keep adding or removing these individual machines or nodes from the cluster. So it is highly scalable, horizontally scalable, without any impact to the existing cluster. So you can keep adding as many number of machines as the data grows horizontally to make it a cluster, right? Highly scalable cluster. So it provides high availability with no single point of failure. So which means that if any node fails, the remaining nodes will be available and can take over the functionality of that node. Okay. So if data is also distributed, when it is distributed, we also have a replication. So data is also replicated across the multiple nodes. If one node goes down, another node can also can serve the data from that node for wherever that wherever the data copy of the data is stored. Okay. So reads and writes. So let's see what the structure is like. So it's called a ring structure, okay, where each node, all the nodes form a ring-like cluster. Why it is not a ring-like is it's a peer-to-peer architecture. What it means is that you don't have a master and slave relationship in the Cassandra cluster. They are all peer-to-peer. Any node can talk to any node. They can communicate between themselves, and they can act as a cluster. And there is no master or slave. So that's why it's a peer-to-peer architecture. Now, if you see all these nodes, N1, N2, 3, 4, 5, 6, all these are nodes. If N3 is down, okay, then the other nodes in the cluster can take over the functionality. They can serve the functionality without N3. Okay. So what is the design goal? I'll just keep it brief, the architecture point, okay? The design goal is to handle big data workloads across multiple nodes without any single point of failure. So across multiple nodes, you can read or write from any of the node. Okay, so you can write to N2 and parallelly read from N6. So the internal replication will happen, and all nodes will be in sync with the data replica. Okay, peer-to-peer distributed system across its nodes, and data is distributed among all the nodes in a cluster. Okay, all nodes in the cluster play the same role. Okay, each node is independent, at the same time interconnected to other nodes. So each node is independent. Every node has the same role. Okay, and they are independent and they are connected to other nodes. Okay, each node in a cluster can accept read and write requests regardless of where the data is actually located in the cluster. Okay, so if the data is on N6, you can still read it from N2. Okay, it does not matter that you have to connect to N6. Okay, you can connect to any node, and internally it will be redirect to the closest node where your data is your data process. Okay, and it will serve from that node. Also, you can write to any node. You can write to N5 and then read from N2. Okay, so any node can accept read request. Any node can accept write request. It's not that there is a writing nodes that are specific for writing or reading, right? So all the nodes are independent and connected, and you can read and write from any of them, any of these nodes. Okay. When a node goes down, read-write requests can be served from other nodes in the network. Okay. So this is the high-level architecture of Cassandra. Okay, and Cassandra has so what does it have? It is more like it's much similar to your RDBMS SQL to interact with Cassandra. It also has a SQL shell. Just like for Hive, you have HQL, right? So for Cassandra also there's a language where you can talk to with Cassandra called CQL. Okay. So we will come to it. I'll show it to you. Before that, so come back here. So this was Cassandra was initially developed at Facebook. Okay, just like Hive, Cassandra was also developed by Facebook initially to power their Facebook inbox search. Now it is open sourced and it is highly used with many of the tech firms like Netflix, Apple, etc. And they have thousands of nodes cluster. Okay. The Apple has close to 65,000 node cluster, which has the Cassandra implementation, which they use for their iTunes. So also the Cassandra is more suited for high write throughput, where there are heavy writes to the database, though it can support reads as well, but it is more generic, high intensity writes to the database, because you can write to practically any node in the cluster, right? So the writes are shared, and high intensity writes can be done with Cassandra. So it's mostly suited for the time series kind of data. Uh, for example, the weather data, where you get weather related readings, or the network related data, or the sensor data, where you get at each point of time you get thousands of attributes, n-dimensional data at each point of time. So based on the time series, based on each time the data is coming from, the number of thousands of attributes that you read for weather, thousands of attributes you get from sensors. So you write it to Cassandra, and the data is coming in pretty frequent intervals. Might be every second or every minute. You get again all the data that is published to Cassandra. Okay. Um, so that is the high level introduction. It's just the introduction I'm touching here. And so you have Cassandra Community Edition you can download. Okay. And then once you download the Cassandra, you just unzip the file. Then you can get started with Cassandra Server. And to interact with the server, just like your SQL client, you get a SQL shell to interact with Cassandra, and it's called Cassandra query language, which looks very similar to this normal SQL language, and it has its own the data types. Most of the normal SQL data types are supported, and then you can create your tables and read and write to them just like in SQL with the Cassandra. Okay, so let's get started. I will show you what if you go to Cassandra here. I'll ping you the URLs. So if you go to Cassandra downloads, okay, I'm using as I said, some old version. You can try with the latest versions, but again, you'll have to see the compatibility. Okay, so you go here, archived older versions. The current version is at 3.3 something, 3.9. Okay, I'm using this 2 to 8 in the demo today. So you can check this 2 to 8 and then download this 2 to 8 bintar.gz, this file. Once you download this file, all you have to do is unzip it. Okay. So once you unzip, you get a file like this. Two to 8. Okay. So if you go to bin, so you get all these files. Okay. So this Cassandra is your server. If you run this, you can start the Cassandra server, and then you have this SQL.sh. SQL.sh is your shell script that runs your SQL client command prompt to interact with your Cassandra. Okay. So let's start with Cassandra. Okay. So to start the Cassandra, we will log in to root su. Password is Cloudera. Okay, and just a /Cassandra. So you have to remember we are using a virtual one node cluster. So there is only one node. And so when we are creating, we have to make sure that. Okay. So where the data is stored? How is the data stored in Cassandra? Okay. So the Cassandra is a columnar database, right? So data is stored as column families. So that we will talk about later when we go to the data modeling in Cassandra. That's a separate topic. But for now, I will just show you the basic getting onto Cassandra, talking to Cassandra, and integrating with Spark. Okay. So when you're talking about it, so you have just like you have a schema in your RDBMS, you create a schema. The same thing in Cassandra, you create something called key space. Okay. And within the key space, then you create tables. Now I have started the Cassandra cluster. Now I will start the SQL prompt, the SQL shell. Okay. So it will give you what is the SQL shell version, what is the Cassandra version. Okay. Now in SQL shell, first let's see what are all the key spaces I have. Describe key spaces. So these are default ones: system traces, system distributed, system auth, system. Haroon DB is the key space that I have created. Okay, so you can create a key space. The syntax is simple. Just say create key space and key space name. You will get the syntax. I will give you the tutorial where you can see the SQL sh commands. Okay, I think you have here. Yeah, like this. The tutorials you'll have to see how you can create uh, the objects in Cassandra, SQL data types and commands. Okay, so if you go here, the first thing you do is you create a key space. Okay, so just create key space and you have to say with replication. You just use this class simple strategy replication factor. Here just use 1, because if you use 2 or 3, it will not work. It will error out because you are using a single node cluster. If you have 10 nodes cluster, then you can choose what is your replication. You want to replicate 2 or 3 or 5, whatever. But since we are using only 1, just use create key space name with replication, simple strategy, and replication factor 1. That's all. Okay, just like this. And then you can go and use this key space. Use key space. So you are in that key space, which means you are in that schema. Now, whatever objects you create, tables, it will be created here. Okay. So just like create table, Arun, you can say column names, name, text, okay, address, text, and then you have to give a primary key column. Just say name is the primary key. So that's it. Your table is created. Describe. Okay. So name text, which is a primary key, address is text, and all your metadata information of this. Okay. Any questions?
So, Karan, so you said these are linear tables, right? So there is no other keys, right? So only the primary keys that you have.
Yeah, you can have composite keys. You can have multiple keys. You can have a structure or a nested structure which can have fields inside that, right? A collection also as a key. Okay, so we will discuss that keys, and it's a small topic. I don't want to go in depth right now about how the data is stored in the columns. What is a column family? What is a row key? How is the data stored against each row key in the column families? So that's a different advanced topic that we can take up later. Okay. So for now, I just wanted to show you how to get into Cassandra, create a table, and then connect it. Okay.
Okay.
Yeah. So this is the table, and let's say I want to go back to Haroon DB. Okay, and describe tables. So these are all the tables I have. So just like this, I can say select star from users. So this is the data. So this is the key, and this is the data you have. It just looks like your normal RDBMS table only. But the major difference lies in the architecture which is the ring architecture, ring model with peer-to-peer architecture, where you can read and write from any node. That's the first. The second one is how the data is stored internally in Cassandra. How with the row keys and the uh, column families. So these are the two differentiators that it has. Differentiator with respect to the other RDBMS, right? But for the user, it almost looks like an RDBMS, like tables you have and the columns and data for now, SQL. So just leave it simple for now, okay? So this is how you start and get connected to Cassandra. Okay, so you just download and install, unzip, and then start Cassandra server with a super user, and then you connect to the SQL SH. So if you want to stop the Cassandra server, you need to, if you say Control C, the system will come out, but the job will still be running. So you'll have to actually kill the process. On this Unix, you don't have a what you call very good way of stopping this server. Okay, so you get this and then say process kill -9 is the ID 447. Okay, so now Cassandra is stopped. Is how you need to stop the Cassandra server. Okay. Anyway, so so that's the first part, to start the server, start SQL SH, and then talk to Cassandra. So let me start the server again. Okay, let's get back here. So that's about downloading and start and SQL. Okay. Now, once you have this SQL table, we don't want to just write from the command prompt. Doesn't make sense to insert and read the data. So what we'll do a Spark connector and then read and write and read data from this Cassandra. Okay. So for that, first you have to check your Cassandra connector project. What is the connector? How do we get the connectors? So last time I have shown you, if you go to Apache Spark, there you have third-party projects, right? And in the third-party projects, there is a Spark Cassandra connector from DataStax. So DataStax is the company that commercially licenses the Cassandra product. It is open sourced. You can use it free, but if you want a commercial license for your production purpose, for support and any issues, then DataStax is the company that is doing the commercial licensing and marketing of the product. Okay, so DataStax also gives the Spark connector for the Cassandra. So this is the Spark Cassandra connector. So there are, as I said last time, right, there are different implementations of the Spark connectors. You can choose whichever you want. So this is the page where it takes you to the project. If you go to Spark packages, just go back here. If you go to Spark packages here and search for Cassandra. There is a PySpark Cassandra if you want to use Cassandra with the PySpark. Okay, and you also have a Spark Cassandra connector for if you want to use with Scala or Java, you can use this Spark Cassandra connector. Ultimately, again, this will take you to the same page, data stacks connector. What happened? It's not opening. Yeah. So this is the Cassandra homepage. Okay. So you have the connector homepage. You have all the versions that are released. Okay. Now, which version of the connector you want to use is what you have to be careful about. Okay. So it gives you the Scala version here. Okay. But the more details of this you will find on the next page that I'll show you. Here you will get the dependency, Maven dependencies. As I said, to download the connector, you need the Maven dependency. So to get the Maven dependency, you just copy this and paste in your pom.xml. The only thing that would change is the version you use here. So how do you get this version? If you go to the home page, which is again this GitHub page, so here you have all the versions. Now, what you have to see the compatibility between the Spark version you are using, the Cassandra version, that is the server you have downloaded, the version, and the Scala version you are using. Okay, so Java is minimum what is required. So currently I am using Scala 2.10 with Cassandra 2.8, right? So 2.8, 2.10, and Java version 7. Of course, this is my old version. In the new versions, I have given you Java 8 installation. So you can go here, you can use this connectors 2.0. So here it's you can use 2.0, 2.1, 2.2. So for Spark here, what I'm doing today, I'm using Scala 2.10, 7. So forget about Java driver for now. So you have to check 2.2, right? Any version of 2.2, Scala 2.10, and Spark 1.6. So the connector is 1.6. So you have to go and download this version, connector version 1.6. So where is this? Yeah. So if you see here, these are all the 1.6 versions again. Okay. So Scala version 1.6.11 to 10 for Scala version 2.10. If Scala is 2.11, you can use this S2.11. Okay. So this version is what you have to replace here. Okay, and then copy it. So for now, what I'm using, the dependency. I'm using the dependency. Do I have it here? Okay. Yeah. So I'm using 161 S210. So this is the version I am currently using. This one, 161 S210. Okay. You can keep trying different versions. based on your compatibility. Then if you get any errors, then you have to try any other version. Okay. Any questions till now?
No, Varun.
Okay. Okay, fine. So this is the Maven dependency. You get. You can copy into your Maven. So another topic um, we need to cover sometime is about the SBT. Here you can see the dependencies you can get either in Maven or you can get in SBT. Okay, so this is SBT dependencies. So the SBT is a simple build tool. This is another way of building your programs. Okay. Sorry. Yeah. Where was I? So this SBT is another way, just like your Maven, to build your projects. Once you write the code, you can build directly from Eclipse using Maven plugins, or you can use through SBT. Hari, I'll have to leave. So I'll probably try to wrap up early so that you can continue your presentations. Okay.
Okay.
Yeah. Okay. So SBT is another. Um, so it's close at 11:50 now my time. So probably we'll close in another 45 minutes, 30 to 45 minutes. I will wrap up this programs and then you can continue. So we will not be delayed. Okay. Yeah. So SBT is another plugin which you use to compile to build your projects just like you do in Maven. That we will cover in one of the sessions with the remaining topics. The major tools, the architectural tools on the big data engineering will wrap up today, and whatever remaining the small topics that we will continue in next 2 or 3 classes, whichever are there, about 30-45 minute sessions where we will do SBT, Spark internals, and if possible the data modeling of the Cassandra. So these are and I have Zeppelin. These are small 30-minute topics. Either me or anybody can cover based on their availability in the next 2-3 sessions. Okay. All right. So where are we? So on the Maven dependencies, I said, so Cassandra 161 S210, this is what I'm using. Okay. So what we'll do, so we have started the Cassandra server. We will just write a Spark program to read and write data to Cassandra, just like we did with Elasticsearch. Okay. So first the connector download we have written Maven dependency for the connectivity. So first we will download import the libraries. Okay. And for Cassandra connector, so we have to import datastax.spark connector. This connector is provided by DataStax. So you can do this. And one more thing is when you come here, GitHub, you get all the documentation for the connectors. Okay. So if you go 1611 connector, not found. So here you get all the API functionality of what is there in the connector. All objects, what they have provided in the connector, you can use, you can check. Cassandra, RDD, table scan, RDD, all of these, replication, whatever functionality, the types, connector types they have, streaming, everything you can check. And these are all the API docs. And you also have a documentation on how to connect with the connector, use the connectors, and then how to read and write data using using the connector, the Cassandra connector. So you have data and how to connect, you can get data with data frames. Today I'm doing RDD based integration. You can also check for the data frame based integration, how you can read and write using a data frame instead of RDD or data sets, which is the after data frames. Okay, so all the documentation is here. Once you go, if you want to explore and read and write more. Okay, so let's go back here. I have the connector library. And then do this. Okay, so logging switched off, creating the Spark configuration, set master, app name, and I have to set a configuration for the Cassandra host. Spark Cassandra connection host. I'm saying it's running on the local host. So normally you would provide host and also any authentication to connect, username, passwords, and port if it is not default port. Okay, so if you don't put this here, your program will get errored out saying that it is not able to connect to the Cassandra. So set this property to the Spark configuration and then create Spark context and the SQL context. So once the SQL context is done, now what I want to do, I want to read the data from file, from whatever file, and write to a table. So which table I have here? Salaries table. Okay, I have a salaries table, no data in this. Now I have a salaries file on my Hadoop. I will read that file and then write to this database. So I'm reading it using Spark SQL. CSV file, which is there at this location. Infer schema true, header is also true. Now what will I get when I read saldf? It's a data frame. Okay, so in the latest versions of the connector, you can also write data frame to Cassandra, but since I'm using the old version, it is the RDD based integration. So I will have to convert this or use this data frame into an RDD, right? And then map to an object, RDD of an object. So to create the object, let's say saldf.rdd. So it will give me a RDD here. So this saldf is a data frame. .rdd will give me a RDD of row. Okay. So once I get this RDD, I am converting this to a tuple, just keeping it in as a group of elements from the row object and converting it into all this string, and the last one is int. So that's how the database salary is integer and all of these are strings. Okay. If you see salaries, so player ID is text, year ID, LG ID, team ID, all this text. Salary is also text here, is it? Okay. So primary key is a combination of player ID, year ID, LG ID, and team ID. Okay. So this is my composite key, primary key, having 4 columns, combination of all these 4 as the key. Now, since I read this, so I get sal RDD of a tuple of 5, string, and int. Okay. Now, once I have this RDD, I will write this to Cassandra. Save to Cassandra. Then it needs key space name, table name, and some columns. Okay. So I give Harun DB. Harun DB is my key space. Table is salaries. Okay. And columns, some columns I'm providing here to match with these. So normally you can also do using a object. Okay. If you create a case class with the object with the columns, you can directly use RDD of that object to save. So this is just one line. So if you look at this, once you have all the setup done, all you need to do is get an RDD and just say save to Cassandra. That's it. With of course the key space and the table name and the columns you are using to save. Okay. So that's the program, integration program. Let's run this job and then we will modify this again to read how to read from the Cassandra and display. So it's connected to Cassandra cluster and processing here, putting the data. See here. So now we get the data that we are writing from our Cassandra. Okay. So data is shown here. 10,000 rows, 10,000 rows to around db.salaries. Okay. Any questions in the integration, Cassandra integration?
So Harun, are there any other ways to push the data into Cassandra, or it's only the Spark to use this?
No, Spark is only one connector. See, Cassandra is a database. Okay.
Correct.
Database, any application can write to database. You just connect to Cassandra and write. So you can write it from Java, you can write it from Scala, you can write it from Python, you can write it from any languages, and you can write it from Spark as well. It's not just exclusive to Spark. Spark, it just gives one connector for the Spark. It's not necessary. Even people can use, normally people use Cassandra as a database. It may or may not have Spark at all, right?
Okay.
All you need is some API to write into Cassandra.
Okay.
So when you have the Cassandra APIs, it's not only for Spark. It's for everything. Okay?
Okay.
Cassandra Java APIs, Cassandra Scala APIs, where you can normally, just like in your projects right now, use it from Java applications, you're writing to Oracle or MySQL, right? Same thing, you will write it to Cassandra also.
Okay. Got it.
Yeah. So that, okay. So that's how you write. Any other questions?
Harun, can you join the users and salaries together in this?
Within the Cassandra, yes, you can join tables.
Okay.
Definitely. So just like your RDBMS, you can join the tables in Cassandra. Yes.
Okay.
Okay. So any other questions? Okay. So once now we have written the data here, we can just read the data also. Okay. I'll comment out this and then say read the data from so I use Spark context dot Cassandra table. So which table? Around DB, sorry, key space, table is salaries. Okay. Sal data RDD dot, just take 20 rows dot for each intel. Okay. So I'm not writing it. I've commented out this part. I can comment out all this. Actually, I can comment out all this part. Okay. Just reading the table, Cassandra table, and then display. Just namespace and table name. Okay, so this is the data, Cassandra row that you get. You display the data from Cassandra. Okay. So that's the reading and writing part to Cassandra using the connector. Now, how do you write using a streaming live data? Okay. So let us explore that part as well. And once that is done, we can take a break, and then Hari and Narayana can do their presentations. So to do the streaming part, what I'm going to do is use our previous class integration program that we did using Kafka and Twitter. Okay. So last week we have written a Kafka producer, a Kafka consumer, uh, Spark Kafka producer, and a Spark Kafka consumer, and then a Kafka console consumer that we read from Twitter, and then we had a producer writing to the topic, and two consumers, one is Spark and one is console, reading from that topic, and then writing to Elastic, right? So instead of that consumer, today we will do a Spark uh, consumer that will write to Cassandra instead of Elastic. Okay. So for that, to store the data, so last week what we had, Elastic Spark, we had a topic called Trump, right? And we were saving to Elasticsearch with Trump/tweets. So to save to Cassandra, we need a table to store, right? So what we will do, first we will create a table, create table Trump tweets with column tweet as text, and I will say only primary key also tweet. Okay, so the table is created. Now I'll go ahead and create a consumer. So to get the consumer, okay. So first, what I have to do, first import the libraries, right? So I have a Kafka Cassandra Spark consumer I'm writing, okay? And then I created a case class called tweet, just like we did here. Tweet, the same thing we are creating here, the tweet. So most of the processing will be the same except the storage part. Okay. So to store here, first we need to, instead of the Elastic libraries, we have to get, of course, we need all the Kafka related libraries, and we have to get the Cassandra libraries because we are storing to Cassandra. So in the Cassandra libraries, one is the Spark connector that we just used in the integration here. Okay, Spark connector. And one is the streaming connector. Okay, that can keep writing data while in streaming mode. So these are the two libraries that we import. And here, what we do, we will first have to read the data from our Kafka topic. Okay, set master, set app name, Cassandra ML batch, and we are also setting the Cassandra connect host, connection host here, that local host that my Cassandra is running. Then we are creating streaming context, and the topic we are reading from is Trump. This is my Kafka localhost brokers. Topic set is just Trump, and I'm creating Kafka utils create direct stream to read the messages from topics, and I'm taking out the message from the topic key and message pairs. So I'm taking out the message from the key. So everything is on my local host. Here my uh, Kafka broker is running on localhost, and my Cassandra server is also running on localhost, obviously on different ports. Okay. Uh, then once I'm getting the Kafka stream, so I'll have to convert it to this object, map it to this object, right? The stream. So from the message stream, for each RDD, I'm taking each RDD and mapping it, split the line, and then mapping the tweet to line of 0, the tweet line. Okay. So new line character, splitting by new line, and then mapping it to tweet. The tweet RDD is now an RDD of object tweet. This is what we want to write to Cassandra table, just like we did for the other in the Elastic. We said save to yes. Same thing here we will do, save to Cassandra. Dot save to Cassandra, and here we will only give the key space and tables. Since we have the object, we don't need to give the columns and write configuration. So here Trump underscore tweets, and let's also print okay. So that's it. We are now reading and publishing to the Cassandra database. Okay. Now, what is it reading from? The Kafka topic. So the data has to be coming into Kafka topic. So we'll have to bring up all the pipeline tools, right? First, we are reading from Twitter. Then we are writing to topic through Kafka producer, through Spark producer into Kafka topic. And then we are reading from Kafka topic and writing to Cassandra. So first we'll have to bring up Kafka. Twitter we don't have to. So Kafka we have to bring up. Then we have to bring up the Cassandra. So Cassandra server is already running. Now we'll have to get the Kafka. So I have to start Kafka here. So I'm already in the root. What I will do here is, where is that Kafka? So Zookeeper is already running. So I'll just start the Kafka server. Okay, so Kafka server is started. Now I will start a Kafka console consumer as well, just to see the data is coming in. I'll start a console consumer to read from the topic and print on the screen. Okay. Now the topic I am reading from is Trump. So since I have given from beginning, these are all the old tweets that we stored last week when we ran the job. That's still there in the topic in the Kafka broker. The log is still there. I don't know what is the retention period I have put, but it's still there, all those messages in the topic. So this is one consumer, console consumer. Then I have Kafka up and running. Then I have Cassandra up and running. Zookeeper is already running. So my SQL. Yeah, so no data here. Okay. Now I will go first and start my producer. Okay. Twitter Kafka Spark producer. This will pull the data from Twitter and put it into our Kafka topic, right? Okay. So as soon as the data is coming here, we will see in the consumer here. Okay. So there are two tweets. Yeah. So it's coming here from. Now we will start our Cassandra consumer, right? So which will read from this topic and write to Cassandra database. Okay, so this is also running. Setting data writing here. Oh, sorry. It has started and stopped. So I have to actually add this because it's a streaming program to say start and then await termination. Okay. So let's get started here. Let's again start the Spark producer. So I will also start this as well. What is happening? Why is it not running? No, it's not running. Oops. Okay. Now let's try this again. Okay. Now it is connected. It is writing 0 rows. Okay. It is not found any data. Now we will go and start the producer. So this will start now putting the tweets onto the topic. Okay, now it's coming in. The data is coming in. If you see here, it says wrote 3 rows, wrote 5 rows to Trump tweets here. Okay, wrote 2 rows. But let's go back and check here. Okay, so here's the data. Now we have both the consumers. One is the console consumer here, which is reading data. One is the Cassandra consumer from Spark. Spark consumer that is reading and writing to Cassandra. And I can also start another one that will read and write to Elastic. This is another consumer that will keep writing to Elastic. So in total, you will have 3 consumers reading from the same topic. One is the Spark Kafka consumer writing to Cassandra. One is Spark Kafka consumer writing to Elastic, and one is Kafka console consumer that's writing to this, that just printing out onto the screen. Okay, so here you can go and see here. So we have 22 tweets here, and let's see if this is, oh, we have not, so we'll have to bring up the Elastic as well, right? This must have errored out. Okay, we can't see that message here, but we have first. CD Elastic. $22. Now let's start the Elastic consumer. So here 23. So the consumer is also writing to Elastic as well. $25. Okay, so a lot of jobs are running on the same node, so it's taking a lot of time, resources to read, but that's it. So you have all 3 consumers reading the data from the same Kafka topic that we discussed here. So we have 3 consumers and 1 producer. Okay, 3 consumers consuming from the same Kafka topic. One consumer is the console that is just printing to the screen. One application is writing to Elasticsearch. One application is writing to Cassandra, and the producer is one Spark producer that is pulling from Twitter the source data and then putting it into Kafka topic. So that is the pipeline. So you can actually imagine that if it's not a Twitter data, or even if it's Twitter data, how the organizations can put it into a Kafka distribution, message distribution, and then read and put in different databases for different departments for their analysis on the data. Okay, So any questions before I stop? I'll stop all of these now. Okay, guys, any questions?
No,
Got this?
No,
Yeah.
No, no, Harun, we are good.
We are good, Harun.
Okay. Okay, good then. So that's all I had to share with you guys today. I hope you all are good with it, clear with what we tried to do, what we achieved in this class. And I will, sorry, last week I did not upload this to FB, but I will just take all of these, zip it and put it on FB or individual files on FB. You can download. Also the pom.xml, it has all the dependencies. But since your version is new, you will have to take each component to the latest version and try it. Okay. Or you can use the old ones, whatever we are using, and try it. But I would prefer you guys to try it out with the new latest versions and the latest features in any of these connectors and tools you have. So since the Java 8 is upgraded on your VMs. Okay. So that's all I have. It's 12:35 my time. Let's take a 10 minutes break. Okay. I will pass on the host, Hema. Who do you want? Is it Hari or Hema?
Left. How much left?
Hello?
you can pass it to him. I mean, when we are starting, then Narayana or myself will take the screen share.
Okay, sure. I am not sure. I
I
don't.
don't think Hema is.
Yeah. I
No,
think.
What happened? How much left?
Anyways, I'll pass it on to Hari.
Okay.
Or Shiva, you can moderate, right?
Yeah, sure.
Okay, I'll pass it on to you. So once we are back from the break, 10 minutes, you can make them host, and once it is done, you can close the call.
Okay.
Thanks, Arun.
Yep. Thank you, guys. Have a great weekend.
Thank you, Harun.
I'll meet you later.
Thank you, Harun.
Bye. Shiva, you have the host now?
Yeah, I got the control.
Okay.
Hello everyone. Hari, Narayana, are you guys back from break?
Yes, sure.
Okay, I'll pass on the control. Hari, you are the host now.
Okay. I hope you are able to see my screen, Shiva.
Yes, Hari. Yeah.
Just wait a couple of minutes for the others to also join.
Sure. I think we can get started, Hari. Just to check, Surya, Leela, are you guys back from break?
Okay,
I
start, Hari.
Okay.
Maybe 1 or 2 minutes.
Okay.
So Harish is there. He's responding on chat. Okay. Yes, Hari. Can start.
Okay. Thank you, Shiva. And good morning to everyone in the US and good evening to the people in India. So basically, I have put a small presentation to take you through this K-means and anomaly detection along with Narayana. So I'll be taking the presentation part of it, and the coding and the remaining part Narayana will take care. So if you have any questions, please ask me at the end of the slide. Yeah. Thank you. So as you know, anomalies are observations that are different from the expected pattern. So these are events which we want to find or we want to analyze more. So in different types of networks or in different environments, we have different anomalies that can occur, which we are interested and some of the patterns or the anomalies that we want to detect normally in a network wherein there is a hacking or an attack, or in a production line there can be some faults wherein some products are coming out of the machine line, out of the manufacturing assembly where they have some defects, or it can be a commercial transaction of your banking, or some online transaction where can be a fraud happening, like somebody is hacking your credit card or your banking details and doing a fraud. So these are some of the anomalies which we want to track and be able to predict. Okay. So why is it so critical? As you know that these kind of transactions or these kind of faulty products or this kind of hacking can cause a lot of hefty financial impact on the organizations or on individuals or on companies. So we want to reduce the impact of this bad outcome, and even it can be also used for detecting possible illnesses. So, like for example, cancer or heart attack. So these are all very critical in terms of the healthcare of people. So these are the reasons why the anomaly detection becomes very critical, and also you can expect a storm or a thunderstorm or these kind of changes in the weather, which can be predicted by using the anomaly detection methodology. So why is clustering good at anomaly detection? It is mainly using an algorithm. So we have a kind of algorithm which can predefine this kind of anomaly detection using a set of data that is already available, and which can be used with a set of simple rules and applying the knowledge of available in the domain. So the domain experts can help us in this way to predetermine the behavior, so that when these kind of anomalies or the uh, different kind of pattern occur, we will be able to predict it. So that is the way how clustering goes up. So what is the meaning of k-mean clustering? K-mean is your applying a simple mechanism, wherein here I'm taking the example of monitoring of the data. Here, for example, we are defining a IP524. Like, it includes the protocol type, source IP, destination, source port, and the destination port. So these are the main 524 information which a flow record has. And apart from this, it will also have, the
Hari, you are not audible. Are you still speaking?
Yeah, even I'm unable to hear.
Hello, Shiva, you're able to hear me?
Yes, Hari.
Sorry, my presentation just popped out, so just give me a minute. Okay, so it has a clustering analysis algorithm that groups objects into k joint or distinct clusters, and these are classified into the same cluster that have similar values. So first we define the number of clusters as per the relevance of the context where we are taking the data, and we initialize the clusters by dividing them all the objects into the k number, the number of clusters that we define, and computing their centroids and verifying that all centroids are different from each other. So this is the step number 2. Then we iterate over the objects and compute the distances to the centroid of all clusters, and we then recalculate the centroids of the modified cluster. So this is the basic process that we do for the k-means cluster. So in order to do this, we use a distance function. It's required to calculate the distance between the two objects, and the most commonly used one is the Euclidean one. It's defined as shown here. So the empirical normalization and weight factor, the Euclidean function. So that function will give you the distance between the two objects. So in the k-means clustering process, results in cluster centroids for normal and anomalous traffic. So if you see, for example, in this case, you have a cluster for normal and a cluster for anomalous occurrences. So in this purposes, we deploy two distance-based classification and outlier detection. Both use the k-means clustering and results, and that can be applied individually or in a combined way. So this is the classification example that you have here. The distances to the cluster centroids of the corresponding traffic class are calculated using the function which I showed before. So an object is classified as normal if it is falling closer to the centroid of the normal cluster. So for example, P here will be classified as normal if it is falling closer to the centroid of the normal cluster, whereas it will be classified as anomalous if it falls closer to the centroid of the anomalous cluster. That is how the classification based detection will occur. So there is also another methodology which is called the outlier detection. In outlier detection, it differs slightly in the way that if you have say for example here if the distance between the object and the centroid is larger than the predefined threshold, that is d max. It says like if it goes beyond d max, then it is termed as anomaly, or it's an anomalous object. So here P2 and P3, you see here in this example, the two objects are lying outside the D-maxer. So they are classified as the anomaly. Whereas P1, if you see, it is still within the circle of the Dmax. Dmax is nothing but your threshold, the maximum predefined threshold max. So which we say like from the centroid, if it is more than say x distance, that is the maximum threshold. So Dmax is a predefined length. So if your P1 falls within that, it is becomes a normal. But since P1, P2, and P3 are outside the circle, outside the Dmax limit, it comes as a both are come as anomaly. So this methodology is called the outlier detection. We can have a combination of these two also. The classification and outlier detection can be used in a combined way to overcome, to complement each other. So both will be complementing each other if they are applied together. So if you see here in this example, both P1 and P2 are regarded as anomaly. The reason being, even though P1 is falling within the Dmax, essentially the distance between P1 to the centroid of the anomaly cluster is less compared to the distance of P1 from the normal cluster. So P1 is essentially closer to the anomalous cluster, and that is the reason why it will be classified as an anomalous case rather than being a normal case, even though it is still coming under the Tmax, the maximum predefined threshold. We still classify this as anomalous because of the distance to the anomalous centroid. So this is a case wherein we are combining both the classification methodology as well as the outlier to arrive at a decision or a prediction. So that is the in brief what I had to present today to you. I hope I was clear, and if you have any questions, please.
Hari, yeah, it was clear, Hari. So what are the probabilities of, false positives in this prediction?
False positives could be the case wherein, how we classify here. For example, in this classification model, if you say these inside the normal what you classify and inside the anomalous what you classify, uh, even though here we are showing it as a distinct cluster, in reality it may be like certain values that we may wrongly classify as normal, but actually it may be anomalous. Like for example, how we took this when we took a combined case, even though P1 is actually closer to the normal, we actually, since it is falling, the centroid is closer to the anomalous, we eventually classify it as anomalous. But in this case, we would have taken this P1 as probably normal. We would have included that point P1 also in the normal cluster. So that those kind of probabilities are there.
Okay. Okay, sure. So it can be done for both real time and for the historical data, right? Or we are going to see only.
See, this is the classification. This is for our training model. What we are having based on our classification. Then, for example, when we on a real-time case, when we take P1, for example, then first we do the classification of the normal and anomalous clusters into k number of clusters, and then you pass the values P1, P2 on a real-time basis to arrive at the detection.
Okay, Hari. Thank you.
Any other questions? If not, I will pass the control to Shiva so that Narayana can take over the rest of the presentation. Okay, Shiva, I think I'm done with my part. So I can you can give the control to Narayana.
Yes, Hari. Thanks for the detailed discussion. It was very interesting. Thank you.
Thank you.
Hari, can you pass the host access to Narayana?
Okay.
Sorry, pass the control to me.
Okay. Done, Narayana.
Can anybody hear me?
Yeah, we can.
Yes. Yeah.
Yes, Narayana, we can hear you.
Okay, thank you. Okay, thank you. Now I get the data from Databricks Cloud and I clean, prepare, and manipulate the data. I have two data sets. One is training data and test data. So I'm not going to split anything. And then I build the model on trained data. Then apply the test data. And then if there is further improvement, then we will go for improvement. Now I'm going logging to Databricks. Now our aim is to cluster data into groups and also find the anomalies which are present in different clusters. Now the first step is we are going to import all the libraries which are needed for k-means clustering algorithms. So let me run this. Now the libraries are imported and also executed. Now we are going to read the file from cluster trained data by using method text file. We are taking from FC and we are getting the file into raw trained data. The first 10 rows will be printed out here. Here we are showing two-dimensional variables, and the last column is it is like a categorical variable, which means which dimensions are belong to 0, which dimensions are belong to 1, 2, and so on like that. Now I want to see the type of raw train data. So I will run this. Here the type is RDD. Now I want to split the data into vector. Now I want to split. So we are taking raw train data dot map of lambda. Here lambda is anonymous function in Python. Of line, that means input. Output is line dot split of comma delimited. Simple example we can show in Scala here above. Well, raw data train array is equal to raw train data dot map of line to line dot split. Why we are splitting to convert from RDD to times vector. So we split it into 3 columns, and the last column is ignored because we are using unsupervised machine learning algorithm. So raw train data dot map of a line, that means input to converting vectors dot times. That means we are converting to times vector of first column and second column. I want to print those data. So for that, for x in train data dot take of 6 rows, I'm printing. Here the first 6 rows are printed of 2 simple dimensions x and y. The same thing we are applying for text data also. Let me run this. Now my train data and test data is ready. Now I want to build the model on training data. So with the help of hyperparameters. Now I'm creating model. Here model is equal to k means here method using train on training data. Shown is the cluster number with maximum iterations is equal to 10. Initial mode is random. That means we are choosing the points randomly. Simple example I can show you. From the picture, it is clearly shown that the number of iterations are taking place. The points are moving from place to place. Here you can see the centroid point. Imagine that there are 3 clusters. From this model, we can predict the cluster number, centroid, and the distance between centroid to every input within the cluster. Based on the model, we can define as center is equal to model dot cluster center. We are going to define the centroids in each and every cluster. Here the shown centroids are printed out. 1, 2, 3, 4, 5, 6, 7, because we have given 7. Our model is ready. Our model is ready. Imagine here there are 4 clusters. From the training data, we can identify the centroid, the distance between centroid to maximum distance for anomaly, and also centroid, the distance between centroid to each and every input within the cluster. In each and every cluster, we can find out. Before that, I'm using helper function. Simple helper function. Here we are defining the distance between 2 points. the distance between 2 points is square root of x1 minus x1 whole square plus y2 minus whole square. According to the formula, we define the distance between 2 points in Python here, and also the distance to centroid. Here data mean input points and model. From the model, we can predict the cluster number of any input. Based on the input points, we can predict the cluster number. That particular cluster number, we can find out the centroid of that cluster. And here we got centroid. We got the centroid, and that particular input point, we can find out the distance between input point to centroid. That can be returned as distance to centroid. Out of all the distances, we can find out the maximum distance. We can find out the maximum distance to that is maximum threshold. Now the training data is over. We calculate the centroid. We calculate the centroid. We calculate the maximum threshold. Now we are applying the test data on this model to find out the anomaly. Now anomaly is equal to test data dot filter, mapping from distance to centroid. That means filtering the distance to centroid is greater than maximum threshold minus 5. That means suppose maximum threshold, this is the maximum threshold, minus 1 means here minus 2, minus 3, minus 4, minus 5. The centroid to minus 5. You can say remaining all the anomalies. So let us print out. The anomalies are printed out here. Now I'm defining cluster code to find out the optimum value of multi clusters. That means number of clusters. That means the number of value range from 15 to 30. Till now we have taken cluster number of clusters as 7. Number of clusters as 7. For multi clusters, we are taking from 15 to 30. The output value is printed here. I will show you the simple example. You can see the graph between X and Y. Here number of clusters are from 1 to 9. Average value is 0 to 90. You can see the graph. We can find out the optimum number of clusters as 3. That's it. I can present like this. Any more question till now?
Excellent, Narayana. Very well done. Thank you.
Thank you. Thank you.
Thanks, Narina. The session was very good.
Yes, no, very helpful. You did great.
Yeah. Thank you.
Thank you.
Thanks, Narayana. It was a good one.
Thank you. Can I stop share or close?
Mm,
You can pass the control back to Shiva, I think.
Okay. I passed the control to you. You.
I think, Narayana, you gave me remote control access.
Yeah.
You have to make a host. So
Oh, okay. Close the. Okay.
just go to participants and right click and then make a host.
End meeting, right? End meeting.
Let's check.